Let's talk about embedded systems now. Your textbook defines embedded system as any device that includes a programmable computer, but it's not a general purpose computer in itself. So the keyword here is that an embedded system is not a general purpose computer. It can be programmed to do something, but not everything that a general purpose computer can do. Let's take a look at alternate definition, which includes more aspects of an embedded system. So a computing system which is specialized for only few applications with none or minimum end user programmability embedded into a larger product. So let's break down this definition and see what are the key features here. So what we see here is that embedded system is specialized only for few applications. This goes back to the textbook definition that it's not a general purpose computer. It's designed to execute only a few applications, not everything. Second, that it's not programmable generally by the end user. So the developers and the designers of the embedded system, they program it and give you as a product. When it's with the user, they are not supposed to be programming this embedded system. And finally, they are generally embedded into a larger product. And you do not buy this product because you want to do some computing. You don't really buy an embedded system, you buy a product, and embedded system happens to be just a part of that product. Let's see some example of embedded systems. So a washing machine that you have at your homes is an example of embedded systems. Now you buy the washing machine to wash clothes, not for doing any computation, but computation does play a very good role in the overall operation of the machine. For example, it decides maybe how much detergent to use, when to let the water in, when to drain the water, how much should be the speed of spinning the clothes, and etc. etc. Similarly, a car, not even an autonomous car, rather a regular manually driven car, has lots of embedded systems. An example could be your braking system. So when you apply brakes, how much pressure should be there on the wheel so that it stops. Another example could be maybe the temperature control inside the vehicle, or maybe the fuel injection. So when you press the gas, how much the valve should open so that the speed of the car corresponds to the fuel that is being injected, and etc. etc. Similarly, you have smart homes where embedded system plays a role in deciding maybe the lighting inside the house, or maybe maintaining the temperature, and so on. An aeroplane has maybe hundreds of embedded system inside it to control its operation. One example is your entertainment system, and again, maintaining the temperature and pressure within the aircraft. And nowadays, Internet of Things is emerging, which is basically a bunch of embedded systems connected to a network and talking to each other. Now, if you see, all of these components have some computing in them, but you do not buy any of them because you want to do computing. You buy them because you want to do something else, maybe washing clothes, transportation, etc. But computing is an essential part of that, and this is done by the embedded systems inside these products. So the kind of information processing that is done by embedded system comes with many names. Cyber physical system is the term that defines that there is a physical world and a digital world, and they are connecting with each other, and embedded system is doing some operation over there. Maybe it's observing something in the physical world. What it observes is then processed upon in the digital world, and it's then again influencing the physical world. Internet of Things, we have already seen, they are just a bunch of embedded systems connected to each other via network. Similarly, there are other things like Internet of Everything, the fog, Industry 4.0. This is basically a bunch of embedded system controlling the industrial processing and industrial setups, etc. So lots of different names. Don't get bogged by them. It's just different names describing the same concepts, maybe in different environments or with some minor differences. Okay, so now we know what embedded systems are. Now let's see among different type of computing systems, which ones are most which ones ship most number of units every year. So we have servers, personal computers, mobile devices, and embedded systems. Now, before you go ahead, pause the video for a moment and just think about it. Which one do you expect to be shipped the most every year? So let's see. Servers, personal computers, and mobile devices. Since only few big organizations need servers, they are shipped the least. Personal computers, maybe every household has one or two computers, so they are more than the servers, but still less than mobile devices because maybe every person has one or two mobile devices. For example, you carry a smartphone, a tablet, etc. So that's why mobile devices are shipped more than the personal computer. But embedded systems, they outperform all of them. The most number of computing devices that are shipped every year are embedded devices because each household maybe has hundreds of them. It's there in your television, it's there in your washing machine, it's there in your microwave, car, they are just everywhere. So that's why they are the most dominant type of computers that are shipped every year. Now, we have seen that embedded systems are very useful in current scenario. So what about their future? Are they going to be important in the future as well? This slide shows 12 potentially disruptive technologies that are going to be relevant in the future. And out of these 12, embedded systems form essential part of 7 of them. We have already seen Internet of Things, autonomous cars, but the things as diverse as robotics, even energy storage, renewable energy, and 3D printing, they all include embedded systems as their critical components. So embedded systems are important today, and they are likely to be very important in the future as well. Okay, so let's see a graphical view of an embedded system. Here we have physical world where some physical processes are happening. They may be biological, social, or anything. And then there is cyber world where these processes will be observed, operated on, and a decision will be taken how to influence the world so that it behaves or it can be controlled. So this part of the figure where we are observing the physical process, giving this information to the digital system is operating on it and then taking decision on how to influence the physical world is part of the embedded system. So there are three critical things: observing, processing the information, and deciding how to influence the physical world. This encompasses an embedded system. So when you design an embedded system, these are the key objectives that you keep in mind. First one is predictability. Now we know embedded systems are part of bigger products that might continuously be interacting with the environment. And some of these things are very safety critical. For example, a car, an aeroplane, they are very much safety critical things. And you should, when you design a system, you should be able to predict how it will behave under different environments, under different circumstances. For example, when a car is on the road, you should take into consideration what kind of weather conditions might be there, what kind of road conditions might be there. So you need to take into account all possible scenarios where your embedded systems might be there and it might need to handle, and then design a system that you can predict its behavior under any circumstances. And an important aspect here is that you need to do this, you need to do the prediction before the system is actually deployed. Second aspect is dependability, which means that you want your system to be reliable. You want it to behave as the way you expected it to behave at the design time. Efficiency is also very important, and efficiency could be in different aspects. It could be energy efficiency. For example, you should be able to perform operation with as less energy as possible. There are lots of embedded systems that are battery operated, and if it is energy efficient, your battery life is longer. Runtime efficiency means the embedded system should be able to take decisions within a certain deadline. And then there are consideration about weight and cost because you don't want an embedded system to cost so much that the cost of the overall product that it's a part of shoots up. For example, if every embedded system start costing, I don't know, $100, then the cost of your washing machine is going to be so high that you won't be able to afford it. So that's why the weight and cost efficiency are also an important aspect of embedded system design. Now, since embedded systems continuously interact with the environment, they have to be very reactive. And the rate of reaction is determined by how quickly their environment is changing. They should be able to keep pace with the rate of change of their environment. As a result, they are time constrained. That means they need to do the operation within certain time limits. For hard real-time system, if the right answers are coming too late, they are just wrong. For example, if you're driving a car and you need to apply brakes, if your embedded system is not able to take a decision within certain amount of time, it might have catastrophic consequences. So hard real-time system, if you don't get the results on time, doesn't matter if the results are correct after the time, they are considered as wrong because they are not really useful. Now to meet all of these requirements, these efficiency targets and the time constraint, embedded systems are always specialized towards only a few applications. You do only the things that are necessary and just don't do anything else. An example could be, for example, if your application does not require any floating point computation, you don't need to have any floating point unit inside your hardware, and that would reduce the cost of the system, which is one of the targets that we want to achieve with embedded systems. Okay, now let's compare embedded system with general purpose systems. So as we know, embedded systems are designed only for few applications, and these applications are known at design time. So when you are building your system, you know what application you are going to execute on it. Whereas in general purpose systems, they are for broad range of application. When you are designing the system, you do not even know what you are going to execute on it. Think about a personal computer. When you buy it, some application, some games might not even exist, but these systems should still be able to execute those applications that are coming in the future. Embedded systems are not programmable by end user. How many of you have ever tried to program your washing machine, your microwave? I don't believe many. But on the other hand, a general purpose computer should be programmable. From the performance perspective, embedded systems generally have fixed performance requirements. As long as you are meeting the deadlines, you are good. If you give it more performance, it's generally not useful. But in general purpose systems, the higher the performance, you can probably enable more applications. The applications that were just too slow to run earlier, with more performance, they might be very much practical. So higher performance is always welcome in general purpose systems. Then the design criteria. For both of them, cost and power consumption are of course critical design criteria. From the speed, in embedded systems, what matters is the worst case speed, because you always want to meet your deadlines. Whereas in general purpose systems, excuse me, average speed is the measure of how good a system is. In addition, embedded systems also need to take into account size and weight, as we have already discussed, as well as dependability.